Hey everyone. So my talk's titled Stellar Autopsies with an 82-inch scalpel, and you probably have no idea what the hell that means. Hopefully by the end of my talk you have some idea of what I'm referencing, but I'm going to try to demystify it a little bit right now. What I work on as part of my PhD project is studying the interiors of stars. In particular, I'm studying the interior of dead stars, and so this is the stellar autopsy. And the tool that I use in my work to do this is the 82-inch telescope out at McDonald Observatory. And this is a picture of the dome over there. Does this work? Oop. All right, moving along. This is the sun. You should be familiar with this. It provides your daylight. It burns you. The sun has been fusing hydrogen into helium in its core. That's how it generates its energy. It's been doing this for about 5 billion years, and it has enough fuel to continue to do this for about another 5 billion years. But we're going to explore what happens after the fuel runs out. We're going to move away to a safe distance here, and I'll show you what happens to stars like the sun, as well as about 97% of all stars when they run out of fuel. They shed out their outer layers and create one of these beautiful objects called a planetary nebula. But all of the inner material of these stars, the core, contracts down under the force of gravity to create an incredibly dense object called a white dwarf star. We'll draw a little box around that there. So the white dwarf star is the dead star that I study. And just to give you a sense of the properties of these objects, here's a comparison of a white dwarf star with the Earth. The white dwarf star contains about the amount of material in the sun, but it's compressed into an object about the size of the Earth. So compared to the sun, that represents a compression in density of about 1 million times, or the equivalent of taking an adult elephant and squeezing that poor elephant into the size of a marble, right? So that's how dense the material of these stars are. It gets its name, white dwarf, dwarf because it's so small, and white because this intense level of compression causes the star to be incredibly hot. So these things are born typically around 100,000 degrees, and because they have no more of a nuclear energy source, they evolve further by simply radiating away their energy and cooling off over time. So you can see the star here going from a white hot to sort of a yellow hot to eventually a red hot. And so the temperature decreases over the lifetime of a white dwarf for eternity. And when the temperature falls between a certain small range, a very narrow range of temperature, these objects are observed to spontaneously vibrate. And so these vibrations pass through the interior of the star and are affected by the interior of the star. As by observing these vibrations, we're able to understand the interior structure. So most stars are, we can only receive light from the surface, and we can only understand the star from studying the surface. But these stars, we're actually able to probe below. So this field of studying stellar pulsations is called asteroseismology. Astero referring to the star, and seismology borrowing from the term for the science of studying the interior of the Earth by seeing how vibrations from earthquakes pass through different layers. So let's see here. So with white dwarf pulsations, remember that 97% of stars become white dwarfs, and they all cool down uniformly, so they all pass through this range of temperatures where the star pulsates. Because all white dwarfs will eventually pulsate, we can take the things we learn about the structures of the pulsating white dwarfs and generalize them to the entire class of these dead stars. The pulsations, so we've got a animation here that shows what the surface brightness variations may look like as a result of multiple pulsation modes, different pulsation frequencies all happening at the same time in this star. And the color map there shows where the star is momentarily brighter with the blue color, those regions are hotter, and the redder areas are temporarily cooler and therefore dimmer. That bottom plot shows, as a function of time in the x direction, the overall brightness that we would measure if we were to record the brightness of this star with our telescopes. So because these pulsations probe below the surface, they're affected by all sorts of details of the stellar structure, including how much material is in the star, how hot that material is, how big the star is, what that material is made of and how it's distributed. We can determine how quickly the star is rotating, whether and how strong there's a magnetic field present in the star, how the energy is transported through different regions of the star, and how quickly the star is cooling, because the white dwarfs are all cooling off. So we can use measurements of the pulsation timescales to determine all these details of the star that are typically very difficult to ascertain for non-pulsating stars. In particular, we do this through taking time-lapse movies of stars of interest. And just to give you a sense here, if you can't see the axis there, the time scale of these variations is about 10 minutes or so. So that's what we're recording. So I do this work from the 82-inch Autopsies telescope. This is my 82-inch Scalpel. This is the original telescope out at McDonald Observatory, 76 years old. This was McDonald Observatory when it was built, and even though it's a bit old, there haven't been major advances in mirror technology since then. So we can still use the glass there. We just put a newer camera there. Let me see. Can I get this working? All right. So in case you haven't used a telescope before, the way this works is. This is in a dome-like structure, and there's a slit that opens up. And you point your telescope at a part of the sky, so it's pointed at your target, and the light from that star, that pulsating white dwarf in my case, travels down the length, down the tube of the telescope, and it reflects off a mirror on the back here. That mirror has a diameter of 82 inches, so that's what we mean when we reference the size of a telescope. The bigger the mirror, the more collecting area there is for light to fall on. So light comes down the tube, it reflects off this mirror with an 82-inch diameter. It gets bounced up to the front end, and there's another smaller mirror up here. And then the light gets focused down through a hole in the first mirror, and it reaches our camera, which is right here, if you can see this little camera. That's our whole instrument. That thing is able to take images very rapidly, back to back, doing time-lapse movies. It's basically the same technology as you all have in your pockets. It's a CCD camera, so it's just like on your cell phone, but much more expensive. And a night of observing looks like this. So this is like time-lapse inception. I did a time-lapse of me taking a time-lapse. This is the 82-inch dome here, and that's the neighbor, the 107-inch telescope at McDonald. And you can see here how the stars move over the sky as the Earth rotates below it. And you may also notice how I'm pretty much fixed on one part of the sky. You'll see the dome occasionally adjust over as I follow a single star for hours, recording a time-lapse movie of its brightness variations. On this sped up time scale, I think I'm taking something like 30 frames per second, but in reality each of those frames is like a 5-second integration. And I do that for hours. Okay, so that's the general story of how we study the structures of white dwarfs. We've been doing this for hundreds of white dwarfs for a few decades now, and what I'm interested in particular with my work is studying a rare class of white dwarf star called an extremely low mass white dwarf. So for comparison in size, the extremely low mass white dwarf is about 5 times larger. And this is really a counterintuitive thing. So when you take the material of the sun and compress it down so far, you end up in a whole different regime of physics than you're normally used to dealing with. And things get held up not by the temperature of the interior, but by the fact that you can't squeeze material together any closer. This is a quantum mechanical pressure, and it's called degeneracy. And so that's where my nickname, Grad School Degenerate, comes from. It's not because I'm so immoral or something. But one of the weird consequences of this that defies your everyday experience is if you take more material to make a white dwarf, that matter actually takes up less space. So it's not like you have a glass of water and you pour some more water in and that takes up more space. With the white dwarf, the way the structure works with this quantum mechanical structure, these low mass white dwarfs with less than a quarter of the sun's mass are actually larger. We're interested in studying these objects in particular because that story I told you about how white dwarfs are formed from the sun and the planetary nebula, from that story, these objects should not exist. But we do see them around in the galaxy, and so we know that something is causing them to be brought into existence. And the way that we understand this is by the fact that all of the extremely low-mass white dwarf stars are in binary systems. So they have a stellar companion that they orbit together. The reason that these shouldn't exist from a creation from just one star is that if you looked at the star that was going to become an extremely low-mass white dwarf star on its own, that star would have a lifetime of burning, of nuclear burning, that exceeds the age of the universe. So there has not been enough time that ever existed for those stars to run out of fuel yet. And so something else must have caused this. These stars to exist. So the way that we understand this is we look at binary systems. If one of these stars in a close binary system begins to run out of fuel, it can puff up and its neighbor can start to steal the material gravitationally that got too close to it. And that can strip away a whole bunch of mass and leave behind an undermassive white dwarf star. In many cases, that second star then can puff up and have its material blown away, and you'll end up with a system with a couple of low-mass white dwarfs very close to each other in a very tight orbit. I want to take an aside here and mention a very interesting system that I've been helping to observe out at McDonald that is a very close binary pair of white dwarfs. These white dwarfs whip around each other with a period of only 12 minutes. So these are really exciting on like a human timescale to watch the data come in. They also pass in front of each other. So if you look at the brightness of the system, you do your time-lapse movie, you see that things are generally the same brightness, and every once in a while, one star transits the other, and the brightness of the system dips. And so you can watch these stars pass one over the other every 6 minutes, because there's two of them. One interesting consequence of this, and to give you a sense of the scale, the separation between these two white dwarf stars is about a third of the distance between the Earth and the Moon, right? So these are very close to each other. One interesting consequence of throwing mass around with such energy is that mass bends space-time. So everyone here last month should know this. If you have two objects in a close orbit, they actually send ripples through the fabric of space-time that can carry energy away from the system. So this is a direct consequence of Einstein's general theory of relativity. And here you see an example where these stars are losing energy, they're spiraling in towards each other in their orbit, and their orbit is speeding up. We've been able to measure this with this eclipsing white dwarf system. I'm going to show you some of that data so you can see gravitational radiation and general relativity data for yourself. Here on the top, you see what one of these transits look like. This is the brightness variation when you have one star passing in front of the other and causing a dimming of the brightness. Now we can measure more accurately than anything else about a stellar system the time scales involved. Our grasp of time is better than our grasp of photon energies or something, right? So so we're able to pin down this time scale to about 12 minutes, a little over 12 minutes, very accurately. And we can revisit this system every few months and see that relative to this vertical line, which is where the center of the transit would be, if there were no decay of the orbit, the actual measured transit times sneak up on us, show up a little earlier, and that's because the stars are spiraling inwards and speeding up, right? And so there's general relativity for your own eyes. But what my thesis focuses on more are these pulsating stars. And we find that these extremely low mass white dwarfs also pulsate, just like the normal mass white dwarf stars do. So the fact that these objects exist as pulsators was discovered at McDonald Observatory, and our group has found the majority of these stars. We've got about 9 of them now. And why this is particularly important to study is that the process of mass transfer in these binary systems is very complicated, and it's not very well understood. It's a phase of stellar evolution that isn't often observed, and computing models is very difficult. So by using asteroseismology to constrain what the interior structures of these stars looks like, we're able to put constraints on efforts to understand the physics of mass transfer in these binary systems. I want to share with you one of our most recent results for pulsating low-mass white dwarfs, and that is this, what we call a light curve. This is a measurement of brightness over time. This is by far the most energetic pulsations that we've ever seen in a white dwarf star. You see here over a period of a few hours that the brightness varies by an extent of up to 60%. Typical white dwarf pulsations are on order of 1% and usually less than that. And so this is by far the largest pulsations we've ever seen. And we're trying to model and understand what this is, even confirm that it is a white dwarf. It's so unlike what we usually see that we're not certain. We're considering that maybe there's some other type of object we've accidentally discovered in this space. But one model that we're considering is that computer calculations of the evolution of these low-mass white dwarfs show that they may go through a very brief phase where they experience a burst of late nuclear fusion inside of them that causes them to rapidly inflate in size and to grow much hotter before converging back to their normal cooling pattern that all white dwarfs do. And when this happens, an outer shell may occur that is able to drive and trap very strongly these really high amplitude pulsations. So some of our initial look at this suggests that that's what could be going on. I want to mention, so that's my extremely low mass stuff. I want to mention one more thing. I think you guys may have heard of, Jeff told me this was in Astronomy in the News or something a few months back, and this is the this has to do with the result from the Kepler spacecraft. So we're abandoning the 82-inch Scalpel for a second and going for a 55-inch Scalpel in space. And Kepler's a mission that tries to discover and characterize Earth mass planets around solar-like stars. That's the mission. But it does this by taking time-lapse movies of a lot of stars. And that's exactly the type of data that people who work in asteroseismology need for their science. And so we found a pulsating white dwarf star in the field and requested a bunch of data. This isn't a low-mass one. This is more of a typical one. I'll show you the light curve here. This had a press release that Jeff mentioned, Jeff and Rachel mentioned, called Dying Stars Suffer from Irregular Heartbeats. Right? Pretty creative. Not my idea. On the top panel, there's this shows. So we got a year and a half of data, pretty much uninterrupted from space. There's no daytime. There's no weather. On the top panel here, you can see 90 days of data, then 1 month, and then 1 week of data. In particular, I want to draw your attention to these increases in brightness that happen throughout these observations. No one expected to see this. We expected to measure pulsations and to be able to use these great data set to really constrain the interiors of this white dwarf, and we did that. But no one expected to see these outbursts. And so we called these irregular heartbeats in the press release, and that's a lot of fun. We ended up finding another one of these, and I think you can see the details a little better here. In this object, this is also a Kepler object. You can actually see the pulsations in the data there. So that's the regular state where the star is pulsating. And then suddenly one of these outbursts occurs. The star gets brighter overall, and also the pulsation amplitudes get much larger. So we can see just from here that the outbursts affect the pulsations. This means that we should be able to use the pulsations to understand what's causing these outbursts to happen, because that's still an open question. I think it's an exciting question because there's been a long-standing problem with our theory of stellar pulsations. That is that I mentioned white dwarfs pulsate in a very narrow range of temperatures. If you ask someone to calculate what that range of temperatures should be, our best understanding of the physics of pulsations say that that should be quite a wide range of temperatures. We can explain why they start here. We've got temperature hotter over here and cooler over here, like astronomers do. We can explain why pulsations start here. This is like the amount of pulsation going on. We can explain why they start here, but we can't explain why the pulsations stop here. They're observed to stop here. Well, we've discovered 3 of these outbursting white dwarf pulsators now, and they're all right here. So we found a new process occurring in stars right where we knew that our theory broke down. We just didn't know why. So I'm hoping that these new serendipitous discovery turns out to be the key to resolving this long-standing issue in asteroseismology. And that's all I got.
Questions for our grad school degenerate right here.
Pulsations, you showed that they pulse at brightness. Is it also pulsation on the sides of the star?
Repeat the question.
So the question was about if the pulsations in these stars affect the size, basically. With these pulsations, white dwarfs have incredibly high gravities because there's so much mass so compressed that the pulsations that we see are actually they're not global pulsations. They're constrained sort of to the surface. So they're more like a surface wave variation. There is a bit of a perturbation to the surface size, but it's not very large. Yeah.
Right down in front.
I'm just a dumb geologist, so what causes pulsations? Is it a gravity?
So the question was, what causes the pulsations in these stars? And it's hard to go back on this, isn't it? Well, I showed that figure where the pulsations are governed by a certain temperature, right? So once the white dwarf cools to a certain temperature, then we observe pulsations to start. And what's going on there? Ooh, I get there. Is that the atmosphere of the star just gets cool enough for what was the, I don't know why I'm flipping through all this. So around here, around 11,800 Kelvin. Hotter than that, the entire atmosphere of the star is completely ionized. You can't contain electrons to the atoms. At that temperature, once you cool past that, then you can start to have the electrons recombine with the atoms, and you get this phase of the matter called a partial ionization zone, where some of the matter is ionized, some of the matter is an atomic gas. So that configuration, the amount of atoms versus the amount of ions, is highly sensitive to pressure or sensitive to temperature variations, and so any perturbation can start an oscillation locally. So things. So it's that the conditions are such that if you were to offset a part of the star, it would rebound back to its original position, and that restoring force causes locally any perturbations. And in this case, it's often related to the convection in the atmosphere to drive these pulsations.
What about upstairs? Let's see. No. All right. Downstairs. Straight back.
Yeah, so how much is the density of the white dwarf related to the elements within the white dwarf, and therefore is the pulsation related to the density of the elements being given off?
I'm not sure I totally followed that one. So are the pulsations related to the density? I can answer that. We actually see, so the pulsations are related most directly to the temperature. And we see that in this, throughout different phases of stellar evolution, we also see different types of stars that aren't as dense as white dwarfs pulsate when they have these sort of temperature conditions that allow them to have this outer convection zone caused by a partial ionization of the atmosphere. So these stars don't pulsate because they're dense. Their pulsation properties are affected by the fact that they're so dense.
All right, one more question right down here.
So what cool name have you guys given to this binary system of 12 orbit?
The question is, what cool name have we given to the binary system with a cool orbit? Well, we call it J0651. But there's actually a little bit of a cuter answer to that. So we typically call things, that's related to its position in the sky, of course. The guy who discovered it was a graduate student here before I got here, whose name was JJ. And so internally we refer to it sometimes as JJ0651. So.
And with that, let's thank Grad School Degenerate one more time.